Module 4, Lecture B, Integration and Simulation. By the end of this lecture, you will be able to approximate areas, accumulated quantities, and work using numerical integration methods, simulate simple dynamic engineering systems using time steps and update equations, and compare numerical results against known values, limits, or conservation checks. Numerical integration. Riemann sums. Riemann sums approximate area or accumulated change by breaking an interval into small pieces and adding the areas of rectangles. Each rectangle has a small width and a height taken from the function's value at a chosen point. For a changing rate, such as speed over time, this estimated area represents a total amount, such as distance. This method is useful when the exact area under a curve is difficult to calculate. A Riemann sum estimates area by using rectangles, and its accuracy depends on how those rectangles are chosen. Fewer, wider rectangles give rougher estimates, while many narrow rectangles usually give better ones. The rectangle height may come from the left, right, or another point in each interval, which affects whether the estimate is high or low. For increasing curves, left endpoints tend to underestimate and right endpoints tend to overestimate. For decreasing curves, the pattern is reversed. Riemann sums help engineers and applied scientists estimate total effects from data collected at separate points. They can approximate quantities such as load on a beam, work from force over distance, or water volume from flow rates over time. While methods like the trapezoidal rule or Simpson's rule may improve accuracy, Riemann sums show the basic idea of numerical integration, building a continuous total from many discrete pieces. Python code. Riemann sums. Riemann sums estimate accumulated quantities by replacing curved regions with rectangles. Using narrower rectangles usually makes the approximation more accurate. The script begins by importing NumPy for efficient numerical calculations and array handling, and Matplotlib's plotting tools for creating visualizations. These libraries provide the foundation for the computations and graphs used later. The speed function describes a linear change in speed over time. It starts at 12 meters per second and increases by 3 meters per second each second. This model will be used to compute distance with Riemann sums. We set the interval for the Riemann sum from time 0 to 5, then choose 8 rectangles for the approximation. The number of rectangles controls how fine the estimate is, with more rectangles usually giving better accuracy. The code first checks that the number of rectangles is positive, since 0 or negative values are not valid for Riemann sum calculations. If the value is not positive, it raises an error to stop the program and prevent invalid calculations from continuing. The code first finds the time width of each rectangle by dividing the full interval by the number of rectangles. It then creates evenly spaced starting times across the interval and finds each ending time by moving one rectangle width forward. These starting and ending times set up the values needed to compute the left and right Riemann sums. To approximate total distance, we compute left and right Riemann sums for the speed function. The left sum uses speed values at the left edge of each interval, while the right sum uses values at the right edge. In both cases, each value is multiplied by the interval width and added together, using NumPy's sum function to handle the calculations efficiently. Calculate the exact distance by combining the constant speed contribution, 12 meters per second over 5 seconds, with the variable speed contribution, 1.5 times 5 seconds squared. Then compare the right and left Riemann sum estimates by taking the absolute value of their difference, which shows how far apart the two approximations are. The output summarizes a linear speed model over time and shows how distance is estimated with a chosen number of rectangles. It reports the left and right Riemann sum approximations, the exact distance for comparison, and the absolute gap between the two estimates, with all numerical results rounded to 2 decimal places. We create a smooth set of time values across the interval and use the speed function to find the corresponding speeds, giving a continuous curve for plotting. To approximate the area under this curve with a left Riemann sum, we use the speed at the start of each subinterval as the height of each rectangle. Set up a clear plot, then draw the smooth speed curve using the calculated time and speed values. Add the left Riemann sum rectangles as semi-transparent bars, placing each one at its left time, using the matching speed as its height and the calculated time interval as its width. Aligning the bars to the left edge accurately represents the left Riemann sum while keeping the curve visible. The plot is labeled to show time in seconds on the x-axis and speed in meters per second on the y-axis. Its title identifies it as a left Riemann sum approximation for distance, and a legend distinguishes the speed curve from the rectangles used in the estimate. The code ends by calling the Matplotlib show function, which displays the completed plot. This lets us inspect the speed curve and the rectangles used for the Riemann sum approximation, all together on the screen. This script uses Riemann sums to approximate the distance traveled by an object whose speed increases linearly as 12 plus 3 times time. Over the first 5 seconds, it estimates the area under the speed curve with 8 rectangles, comparing left and right Riemann sums to the exact distance. It reports both estimates, the exact value, and the gap between the two approximations, while a plot of the curve and left rectangles shows how numerical integration represents accumulated distance. Trapezoidal rule. The trapezoidal rule estimates the area under a curve by connecting data points with straight lines and using trapezoids instead of rectangles. It is useful when a function is difficult to integrate or is known only from measurements. By averaging the values at the start and end of each interval, it assumes a linear change and gives a more realistic estimate, such as for distance from changing speed over time. The trapezoidal rule estimates a total by adding the areas from many small intervals. Using more intervals makes the straight line approximations follow the curve more closely, improving accuracy. It is useful in engineering and physics for turning discrete measurements into estimates of continuous quantities, such as flow volume or energy use. The trapezoidal rule works best when the curve between data points is close to a straight line. Strong curvature can cause the estimate to be too high or too low, depending on the curve's direction. Using points that are closer together reduces error, but requires more computation. Overall, it is a simple and useful method when exact integration is difficult. Python code, trapezoidal rule. This script shows how trapezoidal numerical integration can estimate total distance traveled from speed measurements. It then compares the estimated distance with the exact value to assess accuracy. The script begins by importing 2 key libraries, NumPy for efficient numerical calculations and array handling, and Matplotlib's plotting tools for creating visualizations. Together, these libraries support data analysis and graphical presentation. We use NumPy's linspace function to create 6 evenly spaced measurement times from 0 to 10 seconds. These times mark when speed is measured and provide a simple timeline for the integration process. The speed changes over time, starting at 3 meters per second and increasing steadily. At each time value, the speed is found by adding a linearly growing amount, based on 0.4 times time to the base speed. This check makes sure the time and speed data have matching shapes, so each time value has a corresponding speed value. If they do not match, the program raises an error and stops, preventing later calculations from using inconsistent data. The total distance traveled is estimated by finding the area under the speed curve using the trapezoidal rule. This uses NumPy's trapezoidal integration function with the speed values and their time points. The method approximates the integral by adding the areas of trapezoids between consecutive measurements. We find the exact distance traveled over 10 seconds by integrating the speed function. The constant base speed contributes 3 meters per second times 10 seconds, and the increasing speed term adds 0.2 times 10 squared. Together, these give the exact distance used to compare with the trapezoidal estimate. We measure the absolute error by comparing the trapezoidal estimate with the exact distance. Taking the absolute value makes the error positive, showing how close the numerical integration result is to the true value. The code reports 3 results: the distance estimated with the trapezoidal rule, the exact distance for comparison, and the absolute error between them. Both distance values are shown in meters to 2 decimal places, while the error is shown in scientific notation to make the approximation's accuracy clear. The plot visualizes how distance is estimated from speed data using the trapezoidal rule. It shows speed samples over time as connected points, then shades the area under the curve to represent the trapezoids used for integration. Axis labels, a title, grid, and legend make the visualization easier to interpret before displaying it for analysis. This script shows how the trapezoidal rule estimates distance traveled from speed measurements over time. It compares the trapezoidal estimate with the exact distance from integration and reports the absolute error. A plot also illustrates the sampled speeds and the trapezoid areas, showing how they approximate the area under the speed curve, which represents total distance. Simpson rule. Simpson's rule improves numerical integration by fitting sampled data with smooth parabolic curves instead of rectangles or straight lines. This helps capture natural curvature in changing physical systems, giving more accurate estimates of areas under curves and accumulated quantities from typical measured data. Simpson rule estimates total change, such as distance traveled, from measurements taken at regular intervals. Instead of assuming the data changes in straight lines, it uses a curved model, which can better match real situations like a train speeding up, cruising, and slowing down. This often gives a more accurate estimate for quantities such as distance, water flow, energy use, or work from evenly spaced measurements. Simpson rule is useful for estimating values from discrete data, but it must be applied carefully. It works best with evenly spaced data and smooth behavior, while noisy or irregular data can lead to misleading results. In engineering, the calculation should always be checked against system knowledge, data quality, and expected limits, such as when estimating work from pressure and flow or pollutant levels in a river. Python code, Simpson rule. Simpson's rule estimates accumulated engineering quantities by finding the area under smooth sampled curves. Its accuracy can be judged by comparing the estimate with an exact distance. We begin by importing NumPy, a library used for efficient numerical work with arrays and mathematical operations. It will support later calculations, such as computing distances with Simpson's rule. We use the pyplot module from Matplotlib to create a simple visualization in Python. Here, it will plot time against velocity, so we can see the area under the curve, which represents the distance traveled. The code creates 11 evenly spaced time points from 0 to 10 using NumPy's linear spacing function. These samples provide the points where velocity will be evaluated, setting up the data needed for numerical integration with Simpson's rule. The velocity is defined as a smooth function of time, starting with a constant 3 meters per second and increasing with a quadratic time term. This creates a realistic smooth curve for changing velocity and prepares the setup for applying numerical integration methods such as Simpson's rule. First, count the number of time samples by finding the length of the time array. This matters because Simpson's rule requires an odd number of points to perform the integration correctly. Simpson's rule requires an odd number of data points. If the dataset has an even count, the program raises an error to show that this condition is not met. This early check helps prevent inaccurate integration results. Use NumPy's difference function to find the time gaps between consecutive samples. These intervals show whether the samples are evenly spaced, which is required for Simpson's rule to work accurately. Before integrating, the code verifies that the time points are evenly spaced by comparing each interval to the first one. If the spacing is not consistent, it raises an error because Simpson's rule requires equal intervals for accurate results. The time between samples is stored as the step size because Simpson's rule requires evenly spaced time points. Taking the first difference between consecutive time points gives this constant spacing, assuming the samples are uniformly spaced. Simpson's rule estimates total distance by numerically integrating velocity over time. It uses the time spacing divided by 3, then combines the first and last velocity values with weighted sums of the interior values. Alternating interior velocities are weighted by 4 and 2, giving a more accurate estimate of the distance traveled over the interval. We estimate distance with the trapezoidal rule by approximating the area under the velocity curve with trapezoids. A NumPy trapezoid function uses the velocity values and their time points to compute this estimate, providing a simple comparison with Simpson's rule as another numerical integration method. To find the exact distance, integrate the velocity over 10 seconds. The constant velocity part contributes 3 times 10, and the acceleration part adds 0.4 times 10 cubed divided by 3. Together, these give the total distance traveled. The output reports 3 distance values: the Simpson's rule estimate, the trapezoidal rule estimate, and the exact calculus result, each shown to 3 decimal places in meters. It then reports the Simpson's rule error by comparing that estimate with the exact distance, shown to 6 decimal places in meters. To make the velocity model look smooth, we generate many evenly spaced time values between 0 and 10 using NumPy's linear spacing function. These 200 points give a finer time resolution, which produces a smoother curve for visualization. We compute a smooth velocity profile across finely spaced time points using the same formula as before: 3 plus 0.4 times time squared. This creates a continuous view of how velocity changes over time for clearer visualization. We start by creating a single Matplotlib figure to act as the canvas for the plot. Its size is set to 7 by 4 inches, so the velocity curve, sampled points, and annotations can be shown clearly. This prepares the visualization for explaining distance as the area under the velocity curve. We plot a smooth velocity curve over time to show the continuous model, then add the sampled velocity measurements on the same graph. Comparing the curve and the points shows how closely the discrete samples capture the underlying motion. The fill between function in Matplotlib shades the area under the velocity curve, showing the accumulated distance over time. A low transparency setting makes the shading subtle, so it remains easy to distinguish from the rest of the plot. Label the horizontal axis as time in seconds and the vertical axis as velocity in meters per second, so the plot scales are clear. Add a title explaining that distance is represented by the area under the velocity curve, and include a legend to make the plotted elements easier to interpret. The final line calls Matplotlib's show function to display the completed plot. This opens the figure so you can inspect the velocity curve and the sampled data points, making the visualization ready for analysis or presentation. This script estimates the distance traveled by an object whose velocity changes smoothly over time. It samples a quadratic velocity curve, checks that the data is suitable for Simpson's rule, and uses that method to approximate the area under the velocity curve. It then compares the result with a trapezoidal estimate and the exact distance from calculus, reporting the Simpson's error. A plot also illustrates a velocity curve, sample points, and area representing the distance traveled. Time stepping basics. System state. In a time-stepping simulation, the system state is the key snapshot used to predict what happens next. It includes only the important quantities needed for the model, such as position and velocity for a moving object, or temperatures along a heated rod. Numerical methods update these quantities over small time intervals, so each new step depends on the current state. Choosing a system state for a simulation requires a balance between enough detail and practical simplicity. Too little information can miss important behavior, while too much can make the simulation slow and hard to understand. A good state captures the factors that matter for future behavior and leaves out details that do not affect the problem. In simulations, the state connects the physical system to the numerical calculations. Each tracked quantity should have a clear meaning, correct units, and realistic values, so every step follows reliably from the last. If results become impossible, such as negative tank levels or unrealistic motion, the model or time step needs review. Defining the state carefully is essential for building accurate simulations of changing systems. Python code system state. During simulation, track the system state variables and use update equations to predict how they change over time. Simple checks can then identify states that are unrealistic. We import the pyplot module from Matplotlib so we can create and display plots. This gives us the basic tools needed to visualize data and interpret the simulation results clearly. The simulation begins by storing its starting state. Time is 0 seconds, height is 1.2 meters, and velocity is 0 meters per second. These initial values provide the baseline for tracking how the system changes over time. The simulation uses gravity as a downward acceleration of negative 9.81 meters per second squared. It updates the system every 0.05 seconds and advances through 12 total steps. We begin by creating history lists for time, height, and velocity, each starting with its initial value from the system state. These lists record the simulation state at each step so we can later see how the system changes over time. The simulation repeats for the chosen number of steps. During each step, gravity changes the velocity over the time interval. The updated velocity changes the height, and the time then advances by one small interval. To keep the simulation physically realistic, the code prevents height from dropping below 0. When the object reaches the ground, its height is set to 0, and its velocity is also set to 0, stopping further downward motion. At each simulation step, the current time, height, and velocity are saved into their history records. This creates a complete record of how the system changes over time, which can later be used for analysis and visualization. The output summarizes the simulation by reporting the starting height and velocity, then the final time, height, and velocity with consistent decimal formatting. It also prints how many state snapshots were saved, which helps confirm how many simulation steps were recorded. Create a 6 by 4 inch plotting area. Then graph height over time with markers to show each data point. Label the horizontal axis as time in seconds and the vertical axis as height in meters, so the plot is easy to understand. To finalize the plot, add a clear title describing the system state changing over time. Turn on the grid to make the data easier to read, and adjust the layout so elements do not overlap. Then display the plot so the visualization can be reviewed. This script models an object falling under gravity from a height of 1.2 meters with no initial velocity. It updates the object's height and velocity over short time steps, stops the motion when the object reaches the ground, and records the results. It then reports the starting and ending conditions and plots height over time, showing the object falling until it rests at ground level. Update equations. An update equation helps a simulation estimate the next state of a system from its current state, the time step, and the system's physical behavior. It turns continuous change into repeated calculations, such as predicting a vehicle's position from its speed and elapsed time, or a tank's water level from flows over time. This lets the simulation approximate how the system evolves step by step. Simple numerical update equations assume the rate of change stays nearly constant over a small time step. Using the current state, such as temperature and cooling, or displacement in a spring and mass system, they estimate the next change in the system. In this way, physical laws like heat transfer and force balance become step-by-step predictions in a simulation. An update equation is effective only if it matches the physical model and uses sensible numerical assumptions. Poor choices can produce unrealistic behavior, and even a valid model can become unstable if the time step is too large. Engineers look for update rules that respect physical limits, give reasonable predictions, and become more accurate as the time step gets smaller. Python code, update equations. Update equations move a simulated system forward over time, and using smaller time steps usually makes the predictions more accurate. Plots then help reveal the system's changing behavior clearly. We import 3 key libraries for the simulation: Math for basic mathematical functions, NumPy for efficient numerical work with arrays, and Matplotlib PyPlot for plotting the simulation results. The cooling model is defined by 3 key parameters: a room temperature of 22 degrees Celsius, an initial object temperature of 90 degrees Celsius, and a cooling constant of 0.18. Together, these values describe the ambient temperature the object approaches, how hot it starts, and how quickly it cools over time. The simulation uses 2 time steps to study cooling: a 1-minute coarse step for an overall view, and a 0.1-minute fine step for more detailed temperature tracking. Both simulations run for a total of 20 minutes. The function first calculates how many simulation steps are needed by dividing the total time by the time step. It then creates evenly spaced time points from the start to the end of the simulation. These points define when the temperature values will be computed. We create a zeros array to store the temperature at each simulation time step, with one extra entry for the initial state. The first value is then set to the starting temperature, establishing the initial condition for the cooling simulation. In each loop step, the program gets the current temperature for that time point and uses it to find the cooling rate. The rate depends on the cooling constant and how far the current temperature is from room temperature, with a negative sign showing that the temperature moves toward room temperature. This code updates the temperature for the next time step by adjusting the current temperature using the cooling rate and the size of the time step. It then returns the recorded times and their matching temperatures, so the temperature change can be tracked over time. We run the cooling simulation twice, once with a coarse time step and once with a fine time step. Each run produces time values and matching temperatures. Comparing the two results shows how the choice of time step affects the simulation's accuracy. The exact reference curve is found by modeling temperature with exponential decay, showing how it moves toward room temperature over time from its initial difference. The exponential calculation is applied over fine time steps. The final error is then the absolute difference between the simulation's last temperature value and the matching exact value, indicating how closely the simulation follows the exact solution. The simulation reports the update rule, where each new temperature comes from adding the rate times the time step to the current temperature. It then compares the final temperature from the fine time step simulation with the exact final temperature and prints the resulting error. The key conclusion is that a smaller time step makes the numerical simulation follow the exact curve more closely. The plot compares temperature simulations using two time steps against an exact reference curve. The coarse 1-minute data is shown with connected circle markers, while the finer 0.1-minute data is shown as a solid line. A dashed reference curve provides the benchmark, and the time axis is labeled in minutes for clarity. The plot is finalized by labeling the vertical axis as temperature in degrees Celsius and adding a title that identifies it as a cooling simulation using update equations. A grid and legend are included to make the graph easier to read and to distinguish the time step results from the exact reference curve. The completed plot is then displayed for visual analysis. This script models an object cooling toward room temperature and shows how time step size affects simulation accuracy. It compares a coarse 1-minute step with a finer 0.1-minute step against an exact exponential decay solution. The plotted results and final error show that the smaller time step follows the exact curve much more closely, giving a more accurate cooling simulation. State updates. A state update moves a simulation from one time step to the next by applying a rule to the current state. This lets the model predict what happens next, such as future motion from position and velocity or heat flow from temperature. Simulations progress step by step, which makes it possible to track how a system changes over time. A simulation's state update depends on choosing an appropriate time step and an update rule that reflects the system's behavior. Larger time steps run faster, but can miss important events, while smaller time steps capture changing forces and motion more accurately at higher computational cost. Engineering simulations must balance accuracy, stability, and efficiency. Updating a simulation means choosing which state data to carry forward and what to assume between time steps. Many simulations treat conditions at the start of a step as constant, which is reasonable for short intervals but can break down when the system changes quickly. Whether tracking a drone's motion and battery or pressure and flow in a pipe network, each update must produce a consistent snapshot for the next step. Python code state updates. State updates move a simulation forward one step at a time, and smaller time steps can track changes more accurately. In this example, the simulation follows a falling ball. We import the math library to use common mathematical functions and constants needed for calculations. We also import Matplotlib's plotting tools so we can graph the simulation results, such as the ball's height over time, and analyze them visually. We define Earth's gravitational acceleration as 9.81 meters per second squared, then choose a time step of 0.05 seconds. This small step helps simulate the falling ball more accurately by tracking its motion in fine increments. The simulation begins with initial conditions for the falling ball. Time starts at 0 seconds. The ball begins 20 meters above the ground, and its velocity is 0 because it starts from rest. These starting values define the motion that the simulation will calculate. We begin by creating histories for the simulation, storing the initial time, height, and velocity. These records let us track how the ball's position and speed change as it falls. Later, they can be used to plot and analyze the simulation results. Set a fixed step limit so the simulation cannot run forever if something goes wrong. Then, start a step counter at 0 and increase it with each loop iteration to track how many steps have been completed. The loop runs while the ball is still above the ground and the step limit has not been reached. Each cycle applies downward gravity as the acceleration, then updates the velocity based on that acceleration over the time step. Each simulation step updates the ball's height using its current velocity and the time step, representing motion over a short interval. The simulation clock then advances by the same time step, and the step count increases by 1 to track the completed iterations. At each simulation step, we store the current time, height, and velocity so they can be analyzed later. The height is recorded as 0 if it would otherwise fall below the ground, representing the ball's impact. These saved values provide the history needed to plot how the ball's motion changes over time. To check the simulation's accuracy, we compare its impact time with the theoretical value from physics. The exact time is found from the initial height and gravity, while the numerical time comes from the simulation's final recorded time. The difference between these two times gives the simulation error. The output summarizes a falling ball simulation by reporting the starting height of 20 meters and the time step of 0.05 seconds. It then compares the simulated impact time with the exact freefall impact time, prints the error between them, and gives the number of recorded simulation states. A plot is created to show the falling ball's height over time. The graph uses time in seconds on the horizontal axis and height in meters on the vertical axis, with small circle markers for each data point. A clear title and grid are added so the height changes can be visually interpreted more easily. This script models a ball falling from 20 meters under gravity using small time steps to update its height and velocity. It records the motion until the ball reaches the ground or the step limit is met, then compares the simulated impact time with the exact theoretical value and reports the error. It also plots height over time, showing how numerical integration can accurately track motion when the time steps are small. Result checking. Known value checks. A known value check tests a numerical method on a simple case where the answer is already known or trusted. For example, an integration method might first be tried on a rectangle, or a simulation under predictable conditions such as a tank filling at a constant rate. If the method fails these basic tests, it should not be trusted on harder problems. If it succeeds, confidence improves, though more validation is still needed. Known value checks help reveal mistakes that a final answer alone may hide. By first testing a model or calculation on a simple case with an expected result, such as a constant force or steady temperature difference, you can confirm that the method is working correctly before using it on harder problems. These checks act as calibration points, helping separate real model behavior from errors in setup, data, or understanding. A strong known value check should match the key features of the real problem, not just use an easy case. If the problem has rapidly changing data, test cases should include significant variation, and if results depend on step size, checks should be repeated with smaller steps to confirm convergence. This helps build confidence in the numerical method before using it for engineering decisions involving unknown scenarios. Python code. Known value checks. Known values are useful for checking numerical methods because simple test cases can expose hidden errors. When comparisons are reliable, using smaller step sizes should lead to better results. The script imports three key libraries: Math for basic mathematical tools, NumPy for numerical arrays and computations, and Matplotlib pyplot for creating visualizations. We set the curve's interval from 0 to pi and use the known area 2 as a reference for checking numerical accuracy. Then we test the trapezoid rule with 4, 8, 16, and 32 intervals to see how the estimate improves as the number of steps increases. We create two empty lists to store area estimates and their corresponding errors. This keeps the results organized so different numerical methods can be compared and their accuracy assessed. For each chosen number of intervals, we create evenly spaced points across the interval and evaluate the sign function at those points. We then use NumPy's trapezoid method to estimate the area under the sine curve. This approximates the integral by adding the areas of trapezoids beneath the curve. The code measures error by finding the absolute difference between the estimated area and the known true area. It stores each estimate and its error, so the results can be compared later, showing how accuracy changes as the step size varies. The output checks numerical estimates for the area under the sine curve from 0 to pi. It first shows the exact known area as a reference, then prints a clear comparison of interval counts, estimated areas, and absolute errors. By looping through these results together, it presents how each estimate improves or differs from the known value. The code checks whether the numerical method becomes more accurate as the step size gets smaller. It compares each error with the next one to see if the errors consistently decrease. If every comparison shows improvement, it reports that increasing the number of steps reduces error. A plot is created to compare the number of trapezoids with the absolute error in numerical integration. Each data point is marked clearly with labeled axes, a descriptive title, and a grid to support readability. Displaying the plot makes it easy to see how the error changes as the number of trapezoids increases. This script tests how accurately the trapezoid rule estimates the area under the sine curve from 0 to pi, where the exact area is 2. It repeats the calculation with increasing numbers of trapezoids and compares each estimate to the exact value. The results show that using more trapezoids reduces the error, and a plot of the errors illustrates this improvement as the step size becomes finer. Known value checks. Known value checks test a numerical method by comparing its results with simple cases that already have known answers. For example, an integration routine can be tried on shapes with known areas, or a motion simulation can be checked using constant velocity. These tests do not prove a method is perfect, but they help confirm that the setup, units, and basic logic are working correctly. For known value checks, choose a test case that is close enough to the real problem to exercise the important calculations, but simple enough to have an obvious expected result. Examples include constant force in numerical integration, no heat exchange in thermal analysis, or steady inflow with no outflow in a tank model. If the simulation does not match these simple benchmarks, the problem may involve time steps, boundary conditions, or the numerical method. Known value checks are essential for validating numerical methods. Begin with simple cases whose results are trusted. Then add complexity step by step and compare each result to a benchmark. In a braking simulation, for example, you might first test constant deceleration before adding drag or road conditions. If a simple test fails, the full model cannot be trusted. If later tests fail, the likely issue is in the newly added assumptions. Python code, known value checks. Using known values makes numerical checks more reliable and helps catch setup mistakes early. In this example, a simple benchmark is used to verify work integration. We import NumPy to handle numerical computations efficiently, especially with large arrays and matrices. We also import Matplotlib's plotting tools to create visualizations, which help make the results easier to interpret and analyze. We set a constant force of 50 newtons as a reference for the calculations. This gives a consistent benchmark for checking numerical estimates of work against a known value. The travel distance is set to 4 meters, giving a fixed distance over which a constant force moves an object. This value is used to calculate work and provides a benchmark for comparing the numerical integration estimate. We use step counts of 4, 20, and 100 to compare numerical integration estimates. Increasing the number of steps generally improves accuracy, but it also requires more computation. This helps show the trade-off between precision and effort. We find the exact work by multiplying the constant force in newtons by the distance traveled in meters. This gives a reliable benchmark that can be used to judge how accurate later numerical integration estimates are. An empty list is created to store numerical work estimates from the integration process. These stored estimates can later be compared with the exact work value to evaluate the accuracy of the numerical method. The process tests different numbers of integration steps to see how they affect the work calculation. For each step count, evenly spaced positions are generated from 0 to the total distance, and a constant force value is assigned at each position. The work is then estimated by integrating force over distance using the trapezoidal rule. The error is found by comparing the computed work with the exact work, using their absolute difference. Each estimate is saved for later analysis, and a formatted output reports the number of steps, the computed work in joules, and the error in scientific notation. This makes it easy to compare each numerical result with the exact value. We print the known benchmark for work, found by multiplying force in newtons by distance in meters. This reference value is shown to 2 decimal places and is used to check how accurate the numerical integration estimate is. We create a clear plot to compare numerical work estimates with the exact value. The estimates are plotted against the number of integration steps, with markers showing each data point, so the trend is easy to see. A red dashed horizontal line marks the exact work value, giving a reference for judging how close the estimates are. The plot is labeled to make its meaning clear. The horizontal axis shows the number of integration steps, and the vertical axis shows the work estimate in joules. A title identifies it as a known value check for constant force work, and a legend distinguishes the numerical estimates from the benchmark value. The script ends by using the Matplotlib show function to display the completed plot. The graph compares the numerical work estimates with the exact work value, making it easier to visually check how accurate the numerical integration is. This script checks how accurately numerical integration estimates work by comparing it with a known exact value. It computes the exact work from a constant force over a fixed distance, then uses the trapezoidal rule with different step counts to estimate the same work and report the error. The results are also plotted against the exact value, showing how the estimates compare as the step count changes. Conservation checks. Conservation checks help verify that a simulation follows the physical laws of the system, even when the exact solution is unknown. Quantities such as energy, mass, or charge should stay constant or change in predictable ways. If they do not, it may point to problems like a time step that is too large, a weak update rule, or incorrect boundary conditions. In this way, conservation checks act as a practical audit of the simulation's physical reliability. Conservation checks compare how important quantities change in a simulation with what the physical model predicts. For example, a pendulum without air resistance should keep total energy nearly constant, while a tank's water volume should change according to the net flow. If these quantities drift unexpectedly, the simulation may be adding or losing energy or mass artificially. These checks help ensure numerical results remain physically realistic. Conservation checks reveal whether a simulation respects key physical quantities, such as mass or energy, rather than just producing smooth-looking results. In long simulations, small conservation errors can accumulate and distort the outcome. The goal is not perfect conservation, but changes that match the model's assumptions, such as losses from friction. Regular checks help engineers keep simulations stable and physically meaningful. Python code, conservation checks. Conservation checks help reveal hidden errors in simulations. In this tank model audit, the stored volume should agree with the total accumulated flow. We import NumPy to handle numerical data efficiently with arrays, matrices, and mathematical operations needed for the simulation. We also use Matplotlib's plotting tools to visualize the tank model results, making the output easier to interpret and helping check conservation behavior. The simulation uses a fixed time grid with updates every half second and runs through 10 seconds. The total number of time points is found by dividing the end time by the step size, using whole steps and including the initial time. This creates a complete set of times for calculating the system's changes. Before running the simulation, the program checks that the time grid has at least 2 points. If there are fewer than 2 steps, it raises an error to stop the run. This prevents invalid input from causing unreliable model calculations. The simulation first creates a time grid from 0 to the final time using evenly spaced points. It then models inflow as a base rate of 2 with a small sign-based variation, and outflow as a base rate of 1.2 with a smaller cosine-based variation. These changing rates are used to determine the net flow into the tank at each time step. Set up a volume record for the tank across all time steps, starting with an initial volume of 5. Then, find the net flow at each step by comparing inflow and outflow, and use that result to update the tank volume during the simulation. The tank volume is updated over time using a loop and Euler's method. At each step after the first, the new volume is estimated from the previous volume plus the previous net flow rate times the time step size. This gives a simple numerical approximation of how the tank volume changes over time. To check conservation, we estimate the tank's net volume change by accumulating the net flow over each time step, leaving out the final point. We add this change to the initial volume to predict the final volume, then compare it with the simulation's actual final volume. The difference is the balance error, which indicates how accurate the conservation check is. The conservation check reports whether the tank volume is consistent over the simulation. It prints the initial and final volumes, the accumulated net inflow, and the balance error. The volumes and inflow are shown to 3 decimal places in cubic meters, while the balance error is shown in scientific notation to make any small discrepancy clear. To check the tank model's bookkeeping, a very small tolerance is set as the acceptable error margin. The model passes the conservation check if the balance error is smaller than this tolerance, meaning the simulated volume changes are physically consistent. A final message reports whether the check passed. The plot compares simulated tank volume over time with the predicted final volume from the balance calculation. Time is shown on the horizontal axis and tank volume on the vertical axis, with markers for the simulated data and a dashed reference line for the final prediction. Labels, a title, a legend, and a grid make the visualization clear so the conservation check can be assessed visually. This script checks conservation in a simple tank model by simulating sinusoidal inflow and outflow over time. It updates the tank volume with Euler's method, starting from 5 cubic meters, and compares the simulated final volume with the value predicted from accumulated net inflow. A very small balance error confirms that the bookkeeping is accurate. The script prints the main volume and error results, and plots storage over time to visually support the conservation check. In this lecture, you learn to approximate areas, accumulated quantities, and work using numerical integration methods. Simulate simple dynamic engineering systems using time steps and update equations. And compare numerical results against known values, limits, or conservation checks. In the next module, Module 5, we will go over none.
Thank you for your attention. See you all in the next lecture.